Hello, everyone. Welcome to Kafka, the asynchronous microservices runtime for state, scale, and performance. And I guess you're probably wondering what I'm going to be talking about. Kafka's used for many things, and more recently, we've really seen microservices maturing as an ecosystem. And so what I want to do is I want to tie both of them together. I want to give you an understanding of where Kafka came from, how microservices have evolved today, and how there's a natural affinity for how microservices and Kafka actually provide us with a new paradigm where we're seeing distributed computing going. So I'm going to start with a standard definition of what are microservices. So this is from Wikipedia. We all know that Wikipedia is the source of the truth, or perhaps not, but I'm going to use it anyway because I think it's quite interesting. Microservices are a software development technique, a variant of SOA, architectural style that structures an application as a collection of loosely coupled services. And the interesting thing about this is I think most of you in this room know that it didn't start out as that. This whole loosely coupled thing was made by someone who went into Wikipedia and decided to change the source of the truth to say that now we're going to make microservices loosely coupled because that's a good idea. There's many qualities and it kind of changes the ground quite a lot. It changes how you build your application. But microservices, as you all know, have been on this journey probably for the last 5 years, and they're kind of reinventing themselves. Their microservices are changing from what they were 5 years ago. So you have microservices, you have these things floating around, and classically thinking, these were REST endpoints because that's what we were doing at that time, and that's how we thought about migrating from service-oriented architectures into microservices just by making things smaller. So they need to communicate. Now, how do they communicate? So, we said we're going to use REST. If we want to use REST, we want to know where they are, which means we need a discovery service, and it's going to give us an API to talk to. And so far, so good. That's like a hello world. The problem is this is not hello world. This is stuff talking to other stuff, finding other stuff, knowing how to talk to it. And obviously, this leads to a point-to-point coupling. You need to find it, you need to use it, you have an API telling you how to interact with this REST endpoint. But that's the happy path. What happens when things go wrong? What happens if this guy fails? The microservices talking to it, they need to know how to recover because they're talking to a contract, they're talking to an API. It's their responsibility to know how to fix the problem. What happens when it fails? So that the microservice on the top right might behave differently from the one on the bottom left, and the standard behavior in all of these cases is retry, 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 and eventually fail. And leave it to some poor support guy to figure out what on earth went wrong. More importantly, what happens when we change an API and a microservice? The REST endpoint is our contract. Do we need to change the other things that are talking to it? Does that change propagate? How do we build an application architecture that changes over time? Because I've never put a system into production that hasn't changed. If you have, can you please raise your hand? No? That's good. And then we start inventing other things that we thought were needed at the time. Can we provide a generic mistake handler? Is that going to solve our problem? Things kind of start getting complicated. So it's all well and good when we do the happy path. It's when we get to the unhappy path that we're trying to figure out. So I've given you a really simple scenario here. But what we've learned over the last 5 years is scaling microservices is hard. When I add more of them, how do I load balance? What does this complexity bring to me? If I scale them up and they change, Can I do a rolling restart? Handling state is hard. If I've got a remote database or I've got a local database, where does my data live? How do I ensure data consistency? How do I coordinate that? I don't really want to run a database inside each thing, especially if it's temporal. It's going to die and be restarted elsewhere. How do I actually build a system where all of these problems can be solved? And so I work in the office of the CTO at Confluent, and we're founded by the people that created Kafka at LinkedIn. And as part of working in the office of the CTO, we get to look at research papers and stuff. And I stumbled across this the other day. It's called Out of the Tar Pit. It was published in 2006, and it's really funny to read. It's really interesting to read. But the thing you'll notice, at the top, they talk about the software crisis. And with what I've just described with microservices, that kind of feels like a crisis as well. But they're going back to 1968. I wasn't born then, and we had a software crisis then, and we've still got a software crisis now. Does this mean that we still haven't learned? And right in the intro, this is the thing that they say. They say, we believe that the major contributor to this complexity in many systems is the handling of state. And the burden that this adds when trying to analyse and reason about systems. And now this was 2006. We didn't really have the notion of Kafka. We had event-driven architectures at that time. But they're talking about near-side caching and cache invalidation, cap theorem and stuff like that. But we still have this problem of state. And so with microservices and REST endpoints, it kind of feels like we had it all wrong. But we've been developing applications for a long time now. We've been developing microservices for a long time. And we kind of had it all wrong. But what did we actually have wrong? Well, the state management side of things, some of it we actually had right. And this is an interesting Twitter conversation that broke out, I think at the beginning of April, where Charity Majors starts talking about immutability. And immutability is a principle. Now, we all program applications with the concept of immutability, and it's basically, the nice thing about this is we say, this object cannot change. It's immutable. It gives us all these qualities. It means we can share the object between different threads, but the thing that we don't think about of immutability, it represents state at time. It represents the state that was captured when the object was created, which fundamentally is a quality of an event. An event happens at a particular time. You can't change the event. You can't undo the event. So we have this kind of thinking, but the problem that we had is our mutable objects, or our immutable objects, we're putting in databases. And when we think of events, we don't think about a database. We think about something like Kafka, an event store. Something for emitting those events and allowing those events to stream to anything that's interested in them. The funny thing about this is that's how databases work. When you look at a database, when you look at a table, looking at this materialized view, you're not looking at the source of truth. The source of truth is in the commit log. So now we're kind of going back to saying, well, is Kafka kind of giving us the functionality of a database? So what's the big idea? And I published a blog at the end of January. It's called Event First Thinking and How It Changes Everything. And Twitter being what Twitter is. A guy, first response on the Twitter thread was, oh, event-driven architectures aren't new. I was like, of course event-driven architectures aren't new. We know they've been around for a while, but the thing that's changed is the world that we live in. And what's changed? If you go back 20 years, what's really changed? Yes, we have cloud, but we've got all these other things. We've got IoT devices, we've got microservices, we've got mobile, we've got machine learning, we've got all this stuff. And we've got Netflix, right? That changes what we think. So it's not the new technology, it's not the requirements, it's the expectation that's changed. The expectation of how we run a business has changed. And so as you've probably heard digital transformation talked about again and again and again, and you're probably pretty tired of it, it's the expectations of the business. So if you want to build a microservice ecosystem that's going to scale up and down and handle state gracefully, you're not going to do it with REST. I'm not saying REST is dead, I'm just saying it's about using the right tool for the right job. And that's where Kafka comes in. So how did Kafka come about? So pre-2011, LinkedIn was a young company. And as most startups come about, they do just enough to build a business. If you're in the right startup, they won't over-engineer the solution architecture, they will make it work. And that's exactly what was happening at LinkedIn. They were growing really, really fast. And while they were growing, so was their infrastructure. And it was getting messy. And they were adding remote data center sites, and they had slow links. And like a lot of organizations out there, they got complicated to understand. The consequences of changing something became really difficult to know. What happens if my ActiveMQ cluster goes down, or I will need to upgrade it? What are the consequences of change? So Jay and Nehar and Jun, who founded Confluent, they set about creating Kafka. And in 2011, they had designed Kafka, and they had it running at LinkedIn. And what this did, it kind of said, well, if we put a distributed log between everything, we can write to that log, and whatever's consuming those events can do what it wants. It can be disconnected, it can get taken offline, and when it comes back online, it can just pick it up. And that's like a simple thing. The idea of a log is a simple thing, which I'll talk about in a minute. But it kind of opened up a world. And it opened up a world to them of this flexible architecture where they could democratize what was talking to what, how they could scale it out, and then they could evolve the whole LinkedIn application infrastructure. And of course, Kafka then made its way into Hadoop and every other corner of technology out there since then. But it's really interesting that they fundamentally put a stream between everything. And the nice thing about streams is they're composed of events. So I touched on immutability and how immutable objects are a form of event. So an event is something that happened, but more importantly, it's a fact. You can't undo an event. So it's a fact, something happened, we know when it happened. If we ever want to undo that event, we have to write another event that does the reverse operation. And they kind of get us into this world of understanding behavior. But bear with me, because this comes all the way back to microservices. So some examples are, I've got a user signed up, that's an event. I've got an item was sold, I've got a payment, I've got an ad placement. These are events, and if you send these events through a stream, something else can say, hey, I know a user signed up, I know what I need to do. In the REST world, if a user signs up, then the thing that wants to drive the REST endpoint needs to know what the contract looks like. Rather than just sending an event out, it has this coupling, it has this API definition. When we move to the world of events, we introduce some qualities. So we have loose coupling. Parts of your application can be taken offline, they can be upgraded, you can extend the functionality. We've got all this cool stuff that we've been trying to solve using conventional microservices for a while. But probably what's more interesting is not so much the underlying architecture, it's that when we actually start thinking about events first, we go into the realms of domain-driven design and event storming. And I don't know if you guys are familiar with a guy called Greg Young. Greg Young is Mr. DDD. He's finally writing a book after 10 years, and he's got hundreds of domain-driven design YouTube videos out there from the conferences that he's presented at. But because it changes what we are building, because the process of building our microservice application is different, it's a fundamentally different experience. And you get all these other qualities I talked about as well. So to give you some examples, a series of related events is a stream. So this might be a payment coming through, and it might have the same transaction ID. It might be an IoT device. So we have a common key, which gives us our relationship between events, which go into a stream. But there's 3 different types of data that go into a stream. We've got change data capture. So change data capture is something that comes from an external database, or it's something that relates to a table view. So if a row was created, it was updated, or it was deleted, we can capture an event for each one of those. And we can store that in a stream. We can build a table out of it, which is quite handy. The second one, which is kind of more obvious, is a time series. I've got an IoT device, it's telling me how fast my car's going, or it's telling me a door is opening or closing. And then we have domain events. Domain events are how we classically build event-driven microservice architectures. So if I capture some events in a stream, the fact that I'm storing them in sequence and I'm capturing the time, we know when an event happened, we know the event was immutable. By looking at that stream, I can actually get a wealth of information from it. So if I have a user having a good experience at 11 p.m. in the evening and later on they're having a bad experience, we've captured a behavior, even if we're aware of it or not. Because we're storing in a log, we're capturing the facts, it's immutable, we're capturing this behavior, which is very powerful. So that's the first fundamental thing. By storing something in a stream, we said we're recording when it happened, and because they're all stored in sequence, we can go back in time. We can mine that behavior. And then we can ask if that behavior affected other users. We can take that data from production and we can run it in a non-production environment, provided you've gone through the right security protocols. But more importantly, we can ask questions of the data again and again and again. Maybe we want to run machine learning algorithms, we want to calibrate them, we want them to do things differently. Evolvability, we can add new stream processes or microservices that react differently. We can upgrade them, we can change them over time. And in this example, a user's purchasing something, it's going into an inventory management system, it reserves the item, checks the money is in the account, ships the item and notifies the user, and the event comes out at the end. And that's fine. But then we get a new data science department. The data science department go, hey, we want to build some machine learning stuff. And so we add them on the bottom right-hand corner, and then we want to do some inventory checking. So this is quite simple because we're emitting events. We're not talking to REST endpoints. I still haven't gotten to state yet, not explicitly. So when we work with these events and streams, obviously we need a way of reacting to an event and emitting other events or other streams. So these might be our microservices. And you could build a microservice that just looks at something and it cleans it, filters it, and it emits users over 18 or users or people that have come into this room, and it can stream them off to other streams. And if you want to do temporal reasoning, because now we're in the world of having these events and knowing when they happened, if we want to know that the user's experience has changed, we want to build metrics or we want to build some other kind of temporal view of the data, then we can use a stream processor like Kafka Streams. But that gives us another couple of interesting qualities. So we have a conventional microservice, which might be using a consumer to receive events and a producer to emit events. Or we can use a stream processor, which does that, but also gives you a higher level programming semantic that sits on top of it. And with Kafka Streams, this is a really simple code example. Apologies if you can't read it at the back. But this is just taking some user bids, it's chopping them up and counting them. And it's putting them in a K-table. K-table is just like a relational table, in that you have, well, it's a key value store effectively, but as those events change, it emits them off another stream down the end. Or I can build a payment processing system, and I'm very sorry if you can't read all of this, but in the simpler sense, we've got a balance in-flight service at the top, and it looks at every payment that comes through that's keyed by transaction 1, 2, 3, and it just counts the amount of money going through the payment system. And this is the amount of money that hasn't been fully processed. That's why it's called in-flight. Then it rekeys it by Bob, because Bob is going to pay Alice some money. It's going to pay Alice 100 euros. Because it's been rekeyed to Bob, our payment processor over there on number 2 is running a K-table. It receives it, and its job is to have this K-table and update the balances, a bit like a database would. It then takes that same event, rekeys it to Alice, puts it back onto payments in flight with a new key, and that next payment processor receives the event. Might be the same instance, it might be another instance. But more importantly, it's gone to whoever owns Alice, and Alice's balance has been updated. And then when it's complete, it goes to balance confirmed. And balance confirmed just says, oh, I've processed this amount of payments today. And then the value gets taken off the balance in flight. Now, in the old atomic world of conventional transactions and tables, I could do this with a commit within a transaction, and it would work. I can do the same thing in Kafka, but the problem with payment systems is an interesting one because businesses need to get paid. So I'm using this as an example. My background's in finance. A payment processing system in finance is going to have 25 stages of processing. So then you're saying, well, what happens when things go wrong halfway through this? I can't use a simple transaction to commit the change because there's too many stages, there's too many dependent systems. So that's why I was saying at the beginning, when we think of events going into Kafka, we think of those events as being like a database transaction log. Using a temporally aware stream processor like Kafka Streams, you start owning the functionality of what feels like a database. But it also means it's a lot easier to express very powerful semantics like K-tables and distributed queries. And that kind of leads us to the database deconstructed. And so at Kafka Summit in October last year, Martin Kleppmann got up and he gave quite a humorous talk called, "Is Kafka a database?" And if you haven't seen Martin's talks, this is a very entertaining talk to watch. And we've talked about K-tables, we've talked about Kafka Streams. I haven't talked about a database yet. And the reason I haven't talked about a database is because our events are stored within Streams and they're stored within Kafka. So it starts to make the notion of having a database redundant because we're living in this world of streams. So can we think of Kafka as a database? Well, the nice thing about Kafka is, yes, I've got my broker infrastructure, I have my client infrastructure in a number of languages with the producers and consumers. I've got Kafka Streams, I've got KSQL. And with all of these, apart from the producer and consumer, those tables at the end, they can also be used as a persistence mechanism for your K-tables. which means they actually get stored inside Kafka. And then I have things like exactly once. I have correctness semantics and a whole bunch of other things which make Kafka start to feel like a database. And when you talk to people about Kafka, they, hey, it's this messaging thing. And it goes really fast. But the point is, when I talked about time travel and behavioral analysis of storing events, if you think of it as an event store that scales horizontally, then that changes the thinking behind it being a messaging system. And the underlying premise is Kafka is really just a distributed log. And the log is something where we can write an event to the end, and we can have other consumers that read those events. But the log gives us consistency guarantees, gives you this accuracy. And with Kafka, because it's replicated, it takes care of machine failures for you, but it has like a consumer group protocol, which means it can balance what data flows to which consumers and a whole bunch of other things which take a distributed log and make it very, very powerful, but kind of simple. And this is one of the things. How do I make it scale horizontally? So each one of these horizontal rows is a log. These are where my events that are driving my microservices are going. And it's going to take a key for your event, and it's going to hash that depending on what hash or partition assignment strategy you're using. It's going to put it in a bucket inside a partition. And I can have a couple of 100,000 partitions if I really want to. And then I can fire up my microservices and I can receive those events from one or more partitions. And that's what your consumers are going to do. That's what Kafka Streams and your microservices are going to do. So this gives us a sharding strategy. But the other thing, to make our stream processing runtime feel more like a database, we've got this thing called interactive queries, where we have k-tables. And we can go and query them using a REST layer or a gRPC layer. So while we have state being managed within the stream processors, it's accessible. Or I can use a CDC stream, a change data capture stream, to push those events out into Elasticsearch or something like that. And then I can query Elasticsearch. So there's a number of ways of looking at your data. It's not hidden, it's not locked up. What's actually happening with the data? So my stream processor, which receives of an event, builds a k-table. What actually happens behind the scenes? Well, Kafka Streams runs RocksDB, and it uses that for storing the k-table state, but at the same time, it has a change log topic. It emits the set of events onto that topic. It does it at the partition level. And this is very important because it can receive more than one partition. It's going to write a change log capturing the state of each partition that it's processing. So you might have one microservice processing 5 partitions, and you have 5 changelog topics down the bottom. But you might think, well, I've got all these hundreds of thousands of events that it's processed. If I want to use that to rebuild the state, how do I do that? Now, there's this other thing called compaction. And compaction is saying, well, I've got a row being created, it's been updated, and it just uses the last value, so it collapses all the values together, which means we only have the last relevant value, and then we can rebuild that state. Why is this important? So we said managing state and complexity was hard. Managing databases was hard. But what we're doing here is we're using a k-table. Behind the scenes, Kafka Streams is using Kafka like a database with a log on a partition basis. What this means, though, is I can kill that one stream processor, or I can add another, or I can add multiple stream processors. It's actually going to rebalance that data between them. I don't have to turn anything off. The data is going to rebuild the underlying state store rebuild RocksDB, and then I've scaled up. I've gone from 1 instance to 5, which is pretty cool. So that means databases are out the window in terms of building a real-time data infrastructure in Kafka. Some DBAs don't like this, but that's why you have this naturally convergent ecosystem, which is in Kafka, which is very handy. So if we think of all of our data as a stream of events, sorry, I can go back for that one. The slides will be made available at the end. Then the streams become our persistence model. The streams are where our database now resides. So Kafka effectively becomes our real-time database. Kafka Streams becomes our real-time view that our microservices can interact with or maintain. And it's in process, it's local. So we don't have these consistency challenges that we had of like caching data within the process or anything like that. It becomes a simpler world to operate in. So where does REST sit in all of this? So if you go through the domain-driven design process and then event storming, then we end up with a flow. We have a flow of related events that define a business function. And that's a bounded context. Now I'm presuming everyone here is familiar with the bounded context. It's the bounds of a set of related functionality that is encapsulated. And normally you'll have a team dedicated to building and operating multiple bounded contexts. So REST then becomes a situation of putting it at the entry or exit points where you have another system that you cannot control. So that might be an external client, it might be a web client, something that doesn't support data evolution like Avery or protobuf. So REST still has a role to play in the broader ecosystem. So REST kind of goes back to the cell world, it kind of goes back to the peripheries of the monolith. So if we're going to compose a system like this, I've just given you a really simple example with the payment system. And the payment system came from a conversation that I had at a bank in London. It was actually 2018, I said 2019 here. And I was sitting down with a group of architects and they said, well, we've got 800 developers. They all want to use Kafka. They're all excited about using Kafka. But they're all scared of it at the same time because they say, well, when I send an event into the system, how do I know what's happened to it? How do I know it's been processed? I was like, well, that's because you're thinking about REST. If you do something synchronous and it fails, you know it's failed, right? So what do we do about this? The way that we've been developing has shaped the way that we think. We need to do the same thing again when we move to event-driven architectures. And my clicker stopped working, finally. That leads me to 3 core principles that I spoke to them about. So I whiteboarded that payment system for them. The first one is we've got our core business flow, right? That's what we actually develop as a team. And that's fine. And then the next one is instrumentation and observability. Now, if I'm separating different parts of my application architecture because I've got this natural decoupling through using events, then I can build instrumentation and observability to know, A, how much has been processed, how quickly it's being processed, whether or not I need to scale up and down my microservice ecosystem. But the other thing that a lot of people forget about is the control plane. And I was watching a talk by someone at Amazon, and he said, our S3 team has this number of developers, blah, blah, blah. And he said, out of all of Amazon, the largest team are the team that build and operate the control plane. And if any of you have worked on a large system and have had a catastrophic failure, bringing that system up can be quite a torturous affair because other parts of the system are being stressed in ways that they're not normally stressed. And the control plane allows you to do things like start, stop, throttling, and actually control how the system behaves. So our core business flow, the purpose of that is to scale and provide business functionality. And if it doesn't scale, then things go wrong. I don't know how many of you have purchased something and you've been stuck with a little spinner. I don't know if it's taking my money or not. And I had that with the Olympics when they came to London. And we'd spent £1,600 on all these events, and we thought maybe we'll get one or two, and I got the busy spinner. And I didn't know if we got any or none. It turns out the system had crashed, so we got invited to go in the next week when they fixed it. And so spoke to my wife, and she said, yeah, let's get more. Let's buy more tickets for more stuff. So then we put £2,000 of tickets on, and we got every single one. So that's the thing. You want a system that is predictable. You want something that you can trust. So these developers at that bank, they needed to know that they can build a system and they have a mechanism for trusting it. And then the control plane gives them a method for coordinating that system. Right, we're talking about flows of events. If Kafka can deliver these events very fast to your microservices, what is the end result? So then we end up with an architectural view of what have we developed that looks like this. With our payment system in the middle, we have a control plane for starting and stopping the flow of data, scaling it up, scaling it down. We might have dead letter queues or error queues on the right-hand side. And our instrumentation, how fast is the system behaving? Is it meeting my business requirements? So when you start thinking about data as being a key part of building microservices, we start thinking about the flow of that data. We start thinking about how one event here triggers a reaction to others. And if we build, I presented this last year, and this is an auction system, which is for modeling eBay. I won't go through those semantics, but suffice it to say, I can build all of this in Kafka Streams, and I can scale it out massively. I've got bids coming in at the top. Sorry, I've got items being placed for bids at the top, bids against those items down here, stream table joins, and I've got events reacting to all of these. And when you actually start getting your head around it, it becomes pretty easy. And then I've got some serverless functions up on the end. And on the operational side of things, I can implement dead letter queues, error queues, audit logs, application logs, data lineage. We have customers doing every one of these. And Kafka becomes a nice way for them to do that at scale, to throw events into it and then build extensible functionality off the back of that. And then you have other patterns. So as you start building your microservice ecosystem, how do I make this work within the organization? And the nice thing about this that we said about autonomy, evolvability, is organizations are doing this today. And even over the last 12 months, we've seen a massive upswing on the notion of events as a backbone. We also call it the central nervous system. And that is where Kafka sits at the heart of your organization. And it's not a service bus. It's this method of allowing all parts of your organization to go back in time, to evolve independently, but also to scale. And so in this theoretical model, your events as a backbone would have their own common data dictionary, and that's received by each department. And so if you're coming into a pricing department at the top, you might put some analytics library or some kind of enrichment and process it accordingly. But suffice it to say, the whole point of this is what LinkedIn did at the beginning. is they managed to scale the state without actually realising what they were building at the time. But this notion of a central nervous system is something that we're seeing a lot of these days. Error handling. What do we do about error handling? Well, we build more trust, and we do that with determinism, repeatability, and observability, which is quite simple, but when you actually want to understand it, the first thing we do about error handling in any of these systems is prevention. With a fraud detection system, we want to prevent the fraud from actually occurring against... we want to prevent activity happening against an account that's been marked as fraudulent. How do we do that? We do it at the periphery, at the beginning of the bounded context. We validate events that come through. We effectively create a clean room. We have correctness semantics. How do I know something is going to be delivered exactly once? How do I know the behaviour is idempotent? What happens when I need to recover my system? If I'm doing rolling restarts, what's the behaviour of that? If I have a topology that changes? And the last stage you should never get to, but obviously you need to expect the unexpected, is business continuity processes. What happens when things really go wrong? Now, in terms of these principles, obviously, if you can prevent errors, then you always look good. And I think the thing about this is you can build all of these with the patterns I talked about in the operational queue side of things. So we prevent at the bounded context. We look at idempotent behaviour, correctness semantics. An interesting thing about... so I talked about the payment processing system and what happens if things go wrong halfway through. There's this concept called sagas, S-A-G-A, and a saga is basically like a collection of pre- and post-event processing. So as your payment propagates through each stage, it says, what was the value before, what was the value after, what was my action? As I hop through each one, it collects this state. And it's basically building a transaction context. If anything goes wrong, maybe a system's down or maybe it's been invalidated for some other reason, that saga's collected enough knowledge about the series of events that it's propagated between to unwind the behaviour. And that's where you need to get to build these systems at large scale. And obviously, if you get to number 4 and you haven't accounted for rollback or business continuity, then there's probably a go directly to jail on the monopoly board headed your way. There's a few key takeaways. So if we're building a microservice ecosystem on Kafka, we get all of these qualities. But the thing is, okay, we can think of our events as APIs, so we don't have REST interfaces. Our events become something that can evolve over time with serialization protocols like Avery or protobuf. We have that built in. We have the ability to build A/B paths. But more importantly, you go back to domain-driven design and the ability to model for scale when we think about designing systems using events first. We think of streams as a data flow. We think of this like a deconstructed database that's a data-aware runtime for handling state, which means we can evolve our architecture. We can make changes to our architecture, but we can take those events from other environments and we can pull them into a pre-production environment to validate them, to do back testing. Everything that goes through Kafka is a log. It's an audit. We can make use of that. And we can build, what I've described is quite generic. And the first step towards fully embracing it is understanding that these patterns are all usable and reusable. So I talked about building the business process, but the instrumentation and observability, the control planes, the dead letter queues, that's a write once scenario. We can reuse that application infrastructure. Which leads us to this approach provides simplicity. It gives us a way of handling state. It addresses the complexity and scale that I talked about at the beginning. And it provides this convergent data and logic processing paradigm that we haven't had until now. This is a journey. We see this thing unfolding. We see Kafka being used more and more at scale. It's quite crazy in that how good it is. And now I'm down to questions. This is a blog series. Number 4 is currently going to be published next week. It talks about a lot of the principles that I've worked through in this talk. Please feel free to read it and leave comments. So if you have any questions, I don't know how much time I've got. It's counting down. No time for questions. Yeah, come and see me. I'll either be at the booth or come down and see me. Thank you.